Hi, this is Dan McCurry, and today we're going to talk about using enterprise knowledge graphs and the need for high bandwidth memory to the cores of our processors to do really good enterprise knowledge graph traversal. I'm going to talk a little bit about my background in enterprise knowledge graphs and talk about the growth of knowledge graphs, and then go into some of the requirements we have for very fast memory subsystems for these systems. Just a background on me. I'm a distinguished engineer working for a major healthcare company. I've been working in database and solution architecture. I'm a former chip designer, and recently I've been doing a lot of work using generative AI and ChatGPT to enrich knowledge graphs. A very exciting area that's going to really push the need for more and more memory for these knowledge graphs. So what we're going to cover in the next 20 minutes is what are knowledge graphs. We're going to talk about graph traversal using pointer chasing or pointer hopping. We're going to talk about the need for specialized hardware, and I'm going to make a case that high cores with risks really won't do it enough unless we have really great memory systems to feed those, and we're going to wrap up with a call to action. All right, so let's just talk about graph databases. And when I wrote my book called Making Sense of NoSQL, we talked about 6 general types of databases: relational, analytical, key value, column family, graph, and document. And what we found in the last 5 years is that of all these systems, if you have complicated relationships amongst your customer data, product data, licensure data, all these complicated relationships, graph is a very good way to do a lot of that work. And we've also seen graphs increase in popularity. Ever since Google's knowledge graph came out in 2014, we've seen a pretty steady growth in the popularity of graph databases compared to all the other 5 types of databases. Myself, I work on a daily basis in a graph that has tens of billions, not millions, but billions of vertices, hundreds of millions of edges, and we have tens of thousands of concurrent users hitting these databases, for example, from call centers. And what we've done is we've defined what I call the 7 factors that define enterprise graph. And almost all of them are around scalability, making sure we have thousands of concurrent users, hundreds of concurrent applications. We have secure and ad hoc query. We can protect data at the database level. We can scale that database, we can grow it, we can add new nodes to the cluster without ever shutting it down. It automatically rebalances. We have high availability, and we have fine-grained control over who can see what data within that thing, as well as this large suite of graph algorithms to do various traversal of those things. So an enterprise graph is a very different thing than a small project graph. One sample program is this idea of patient similarity. So imagine you have a new patient come into your emergency room or urgent care, and you do analysis of that patient and their background and their symptoms. You have 100 million similar patients in your database, and then you ask, how similar is this to my 100 other million? And how can I get to the root cause of this by doing that comparison and getting them the best care path we know based on all our previous history? We want to do that in milliseconds, not in days. So those are challenging queries when we have so many things that we want to compare. And those are the types of problems that these enterprise graphs can handle these days. At the heart of this is understanding that when we do graph queries and we have a query that's going out to all of these nodes in a cluster, there are some tasks that we have to do sequentially. But in most population level graph queries, that analysis can be done in parallel. We can start a query, we can spread these tasks out, we can assign them to cores on servers across the cluster. Each of them can do their work, find the data, and bring that back, kind of a virtual MapReduce, but within graph. So the more we can parallelize these operations, the faster they're going to be and the faster response time we get. How do we do that? That is the key question that most of the graph database vendors that have really been competitive in the last 10 years have found, that by keeping close to the hardware, what we call pointer hopping or pointer chasing. We can do graph traversal by just using a pointer, have it jump to a different spot in memory, look at the data around there that represents a vertex and its edges, and then continue to traverse. The farther you get away from that native graph, the slower your systems are going to be, and that has huge performance implications. But it can't just run on a single node. These queries need to run on a distributed node of maybe 100 different servers, each of those servers having thousands of cores, each of them carving out a little task, doing that traversal and bringing the results back to the original query node. We have done some of these with full custom FPGAs that are programmed. We can do some wonderful things doing cosine similarity in parallel, embeddings, recommendation engine. But yet today, there is no company that has ever designed a full custom ASIC chip to do this graph traversal. Everybody's using generic processors that have huge instruction sets, and we're only using about 5% of those instruction sets when we're doing graph traversal. So one of the other problems that comes up frequently is this idea of customer 360. What if I had all the information about all my customers every time I touch them, every phone call, every time they visit the website, every time they do a search, every time we have any phone call interactions, all of those things can be put in one integrated knowledge graph. And when they call into our call center, we can bring up that call in the entire history, what we call the member journey, in fractions of milliseconds, and then start to understand the impact of our conversation and help our customers get their problems fixed quickly. And actually now recently enabling chatbots to traverse this data to get the answers out very quickly from a single spot. So these are lots of problems that demand lots of graph traversal optimized for this native pointer hopping. So now let's just talk a little bit about what we mean by this graph performance. And in this chart on the vertical axis, I put graph size from at the bottom, small graphs of maybe 10 million or 100 million vertices, going up to 1 billion, and then tens of billions and hundreds of billions, and up to 1 trillion vertices. And those are the types of things that companies are working on today. On the bottom axis, we have a standard measure of graph throughput. We call these GTEPs, or billions of traversed edges per second. You'll notice I put both of these on log scales. And I want to make sure everybody knows that most companies that are running today are running under this relational database system that requires you to put primary keys in memory, put foreign keys in memory, and then compare them for every single query you do. And what it means is that you're getting about 0.01 GTEPs when we're looking at relationship traversal. Now, you can use a lot of very good databases that were originally designed for single nodes, and you can get some good performance up to maybe at the most 1 billion edges on a single node of a terabyte of RAM. And you can start to get maybe 1 or 2 orders of magnitude better performance. If you start to distribute that is, distribute that same job over maybe 100 nodes, you're going to get 2 orders of more performance as you distribute that. Tiger Graph is a good example of a company that has designed their system from the ground up to be distributed. And then there's another version of that is, what if we took that and did hardware optimization? I personally believe, just by looking at the instruction sets we're using today and what we could be doing if we optimize this hardware, that we can get 3 orders of magnitude additional performance if we had memory subsystems that could keep these cores fed. So that's your challenge. How do we get to this low cost but high performance state where we optimize our hardware and our memory subsystems to work at scale, almost near supercomputer speed, but using off-the-shelf chips and standard equipment that you can put in a standard set of racks in a data center? Just to show some examples of this, I always like to reference LinkedIn. Many people know LinkedIn. LinkedIn runs on a graph called the liquid graph database, and they have about 250 billion edges. They're running well over 2 million queries per second at their peak loads, and they're getting tens of milliseconds latency. So you should know that these systems can scale, and we need those systems to scale to run things like Facebook, LinkedIn, product graphs, and Amazon. Even Pinterest runs on graph databases that have hundreds of millions of edges. Just recently, TigerGraph also published a benchmark on a 218 billion vertex system running on AWS Cloud. But what's interesting about this is they use the standard CISC processors. And what this should tell you is that these systems have never been optimized for graph. And I think even though companies are pushing the limits here, what we can do is we can build systems that are going to dramatically exceed the performance that we're seeing on these distributed clusters. Why is this important? And I'll give you a good example. I always try to anchor this in a real-world problem. And the real-world problem is what I call anomaly detection. When COVID first came out, a lot of us were caught behind because we didn't see these trends coming up quickly enough. And we have a shared vision of all healthcare data going through our knowledge graphs and looking for these patterns. And the more queries we can do in parallel, the more we can detect anomalies quickly and start to put in interventions in place where they need it best. So those are all things where we need these graphs to really scale. So 2 key insights. More cores distributed across a network means faster processing and better parallelism. Keeping these cores from getting starved is a huge problem. If they need to access a subpart of the graph, and remember, we can't use the same predictive models we see in traditional compute. These random pointer hops mean that we don't have the locality, so we need to keep these systems from getting starved, and we need lots of fast memory systems that don't rely on tricky algorithms to predict branches and things. And I just wanted to also mention that we've made great innovation in things with like GPUs. GPUs have great parallelism, but they were originally designed to do matrix manipulation for video games. They've been retrofitted to use that same matrix, or it's called tensor systems, to handle machine learning workloads, but they are not optimized for individual pointer traversal on independent cores. They don't work well on sparse data. They really work well when all of the networks are connected together by everything else. And that's really not the way that we have real data in the world, where a patient may be connected to their chart, but not connected to all the other patients in the network. We need sparse matrix operations too. Just to be very clear, dense matrix operations are fantastic when we're doing things like images, where points in an image are all hooked together. But when we start to look at patient data and diagnosis codes, we have a very, very sparse problem where only 0.001% of these values are non-zero. That just doesn't lend itself to GPUs and using GPUs to solve those problems. So one of the examples that I have for everybody is the Esperanto RISC architecture. Esperanto has managed to put 1,088 RISC cores, 64-bit RISC cores on a single die. And even though it's not optimized for graph, there's a huge amount of horsepower there. But what we need to do is consistently come up with ways to acknowledge the fact that graph operations are unique, are different from traditional machine learning. Now, they work together with machine learning applications. But what we need is more parallelism. And we need to know, can we keep all these cores fed with memory? Secondarily, I also want to emphasize the fantastic tools like that company companies like GraphCore have done. If you take a look at their Pop Vision tools, they have fantastic tools for analyzing how the graphs or other systems are traversing those memories. They've got GraphSage running on them, where they can do independent analysis of IPUs. They can see these execution trace. They can compare different layouts and different algorithms. So you can't just throw out these cores in memory. You have to have good graphical tools for analyzing that data. All right, so to wrap up, call to action. I would like everybody at this conference to reach out to your friends that are working in the field of graph databases and just ask them, what if I could create a piece of hardware that could give you 1,000-fold, 3 orders of magnitude speed up? How would that impact you? How would that impact your business? How could you write queries that would do more work in a shorter amount of time and create better population level analytics, as well as help your customers get their questions answered faster? And then a last suggestion I have is join the new ISO IEC graph, or called the GQL standards committee. That standard should be published this year. And I think that having a standard graph database for all these different systems, standard query language, is going to make a world of difference for as far as adoption. So with that, I want to thank you very much for your time. And if you have any questions, please reach out. I'm on LinkedIn under Dan McCurry, and I'll look forward to talking to you in the future. Thanks.